Alright, so this is the second part of systems of linear equations and matrices, which is Gaussian elimination. And to first explain that, let's look into what echelon forms are. I don't know if I'm saying that correctly. Is it echelon forms? Yeah, so let's say you have a matrix, right? You can follow a few rules for it to be in a certain form. And one form it can be in is row echelon form. And it has to follow a few rules for it to be in this manner. One is if a row does not you can't really see that. Yeah, well, if a row does not consist entirely of zeros, the first non-zero number is a 1. So that means no, I think you get it. It's a good explanation. So that's within a row. Next is rows which only contain the number 0 are all grouped at the bottom of the matrix. And the last thing is every row with every row that starts with a 1 needs to be in the right order, which is that the lower row will have the 1 further to the right. So that means like you see this, oh god, did I change? I accidentally made new page. If you see this, it has to be further towards here, you know, like there. That's not good, but you get the point. Like it can't be straight down, or it can't be like this. It has to be in this direction. That's horrible. It looks horrible. But yeah, it has to be like basically further to the right by at least 1 or more. And if you fulfill those 3 categories, you get row echelon form or row echelon form, whichever way it's supposed to be said. Now you can add, if you fit one more property, which is that each column that already contains a leading 1 will have a 0 everywhere else in that column. If you add that property, it turns into reduced row echelon form. And so this is a good way of thinking about it, right? So this is comparing like reduced row echelon form with row echelon form. Row echelon form, like every row starts with a 1 and each time it goes further to the right. But then above the 1, it's just whatever, right? But with reduced row echelon form, it has that same property of moving to the right, but above is always a 0. Everywhere else in that, like each of these leading one, this is like the leading one, right? Because it starts each row. Each leading one not only like has the zeros in that row, but it's row and column. Now, that only applies when there is a leading one. So if you can have something like this is reduced row echelon form, where there is that -2, but there's no leading one below it or whatnot. So it technically is reduced row echelon form. And basically you should be able to turn any matrix into row echelon form or reduced row echelon form using a few I guess a few like algorithms. And so the algorithm that first converts the matrix into row echelon form is Gaussian elimination. And so this is best explained with an example, but basically Gaussian elimination, in Gaussian elimination, you first pick a row with like a random value like at the front most, bring that to the top, and divide it by a constant until you get that leading one. And then after that, everything else that has any value in that column subtracted by the top row multiplied by whatever it needs to be for all the following values to be 0. It's a bit complicated, but when I show you an example, it'll make sense. And then you just repeat that for every row so that you get all the leading ones and nothing below it. That will bring you to row echelon form and complete Gaussian elimination. So I should have an example somewhere here. Yeah, this. So this. So here, can I? Yeah, that's kind of visible. So here, like this is just like a crazy matrix to start off with. Wait, let me just. Okay, apologies for like the shadows. Wait, maybe I'll turn on this lamp. Okay, so this is just like a crazy matrix, right? And then I indicated like the row operations I put in here, but I can do certain row operations, right? Like this, okay, at the start, it already starts with a 1. That's lucky for me, right? So now basically these two, I want to subtract it by multiples of that first row. So here I did -2, because these two start with a 2, and this is a 1 multiplied by 2, 2 minus 2, that's a 0. That's what we want. So I did that here, right? And you know, you have to do it with all the other elements as well. So once that's done, this is a 1 and everything below it is a 0. Now we go to the next available column and try to find something we can convert to a 1. Okay, that's one thing there. So let's multiply that by -1, so we get like a leading 1. And then we can adjust these two accordingly. And I did that here. So this is a 1, and then these two get subtracted. It's like by 5, by 4, so they're both 0 and adjusted. Now this one's like all 0, so I kind of just have to twist it and like move that to the bottom. And this is the last thing. This is the next column where there is a value that I can divide. So I did that to turn it into a 1, and I moved the 0 down. So this finishes Gaussian elimination. Look up more tutorials for more examples. But that's the first step. The next step is Gauss-Jordan elimination. And what that is just once you've reached this point, like this is row echelon form. If you want to get reduced row echelon form, you just go backwards now. So now I can just take this one, you know, subtract the second row by the third row, subtract the first row by the second row, so that everything above that is 0. And I did that here. These are the operations I did, and it resulted in this. So I get this where each one has nothing to the left of it, so like to the right, and there's nothing else in that column as well. So this is reduced row echelon form. And you might be wondering like why yes, it helps, because if you remember that like a system of linear equations, this represents this. So if you have everything as like I showed earlier, where it's 1 1 1, that just means like x is 4, y is 7, z is -1. Makes it easy. So you might be like, okay, so if you've reached this point where you have to do this, like what's the point anymore, right? Because you don't get that easy transition. This helps with parametric equations. So when I take this out, like these three variables, let's say like x1, x3, x6, they're all individual, and it's best if I draw it up. Hold up. So I can get x1, x3, and x6, right? And then there's other stuff around it. This is x2, so it's plus 3x2 plus 4x4 plus 2, shoot, I turned that into an x, plus 2x5, alright? This is just has that 2, so plus 2x4, right? Simple, easy. This all equals to 0, 0, 1 over 3 based on this, right? So this means this, right? And then we'd be like, okay, well, yeah, see, that doesn't give me a direct answer, but what I mean by making it easy to do parametric equations is when we discussed this earlier with like the T, S, and R, when there are an infinite number of solutions and you can't just directly get the answer, this helps with that, because you can see that these three like don't get repeated, and these are all like the repeat kind of guys, you know? So I can say that, you know, x2 equals to T, x4 equals to R, x5 equals to S, and that means that, you know, x1 equals to, I can push this all to the other side, minus 2t minus, wait, I think this is 3, minus 4r minus 2s, you know? X3 equals to minus 2r, and then x6 just equals to 1 over 3. That's like the only clear one. But then getting this is general solution is much easier. And so that's Gauss-Jordan elimination. So now that you understand Gaussian and Gauss-Jordan elimination, the last thing to explain is homogeneous linear systems. And a homogeneous linear system is basically like a linear system where the answer to every linear equation is 0, right? It literally, it's just this. It's just 0, 0, 0. And there are a few properties to keep in mind with that. But very, very simple rudimentary thing. Like one thing is that in all of these homogeneous linear systems, one answer will always just be like every variable, every unknown is equal to 0. That's a valid answer. And that's known as the trivial solution. But it is also possible after you go through all the process of finding the reduced row echelon form and expanding from there. If that will mean that there are non-trivial solutions. That means there are solutions that aren't just everything is equal to 0. And so when that happens, there are infinite solutions. And so a homogeneous linear system either has that one trivial solution where everything's 0 or an infinite number of solutions. And it's worth mentioning that, okay, wait. I'll bring it to the camera instead of like swinging around the camera. Worth keeping in mind that this part in green, okay, well, you can't see it anyways. The difference between the number of unknowns, right? The number of like different variables, and like the difference between that and the number of rows, the number of equations you have that aren't just 0 equals to 0, that difference is the number of parameters you're gonna have. So if like they're the same, then there's only one solution, that's the trivial solution. But if there is a difference there, and let's say you have 5 equations, but there are 5 equations that aren't 0 equals to 0, and there are 6 different variables, one of those will be a free variable. And that means like the thing where you just assign a random value, like t equals to whatever, and whatever value you give to that will make the linear system valid. But yes, that is the second part, Gaussian elimination, if I'm not wrong. So yeah, I'll see you.